intimidating voice. I told you that you are responsible to know exactly what's happening in your program, which means that I can ask you to come to my office and show me what's happening, especially if you're using other language, but even if not. And I said that, of course, you can consult with other things, including web resources, but you still have to be responsible for your program. And I forgot to say that answers like, it's my partner, not sure what's going on here, that I will not be happy with. So responsible for your program is you personally, it's not her responsibility. So it might be your partner that wrote it, but you still asked to. Right. That's about homework 1. We'll mostly talk about homework 2 today. And before that, was request to show 2 minutes of GeoGebra, how to start with this. So I'd be happy to. And before that, any bureaucratic questions? But it's good with homework 1 that it was originally for today, but then I added a few days. But yeah. Okay. I don't know, 10th, whatever it is. I added 5 days. But it makes it quite close to homework 2 if you are using all of it. So, okay, let's talk about GeoGebra just to be just as a what I found as convenient way to check my deals, but it might be very much due to my ignorance about better tools. So we'll take it for whatever it is. When you go to GeoGebra, my favorite will be GeoGebra Classics. And then usually it shows you the 2D view. And now you can define, say, a point and another point. And another point by clicking the point and create them. The naming is automatic. You can change it, but the name is automatic. I can also create another point F by going to the algebra part. They call this part of the window the algebra part, and define another point, say 1, 1. And the understanding about the name when I'm typing it from algebra is I use capital letter into the point that I just defined, or if I use the same thing as 1, 1, but without spacing anything. So if I'll now change it to V, it's the understanding. Right from the beginning, V equal 1, 1, and voila, it created. That's how I create a vector. And if I'll ask what is a point A plus B, box, and I can write a vector vector D. And if I want a vector from point to point, it just visualize that the vector is of course the same, but if I ask from a vector D. D. Now I show it over here instead of starting from the origin. Is too loud, and the about GeoGebra is that it keeps everything updated all the time. The line just appeared. I didn't have to say. Since I used the letters Y and X, the understanding is that that's the also what are all the points Y times V, this vector V that we just defined, equals 0. And I'm going to call this one a coordinate. So that is the thing where they were xy that they want to know about all the points xy. They satisfy this equation. If I'll ask about all the points xy, that is x squared plus y squared equals 1, and the answer will be, I'm going to write equal 1, but I don't want it to appear before you tell me. x1 plus y, we'll use it today, x squared plus y squared equal 1. It's just a circle around the origin. And voila, it appears, and I can define a slider, say s equal a slider between -1 or 1, or if I'll just write s equals 3, it will actually give me the option to have a slider of this type. And if I'll ask, instead we'll change the squares that I had beforehand into x squared plus y squared equal s squared, then now my circle is of radius s squared. And by controlling it, it will change the radius. As I said, everything is updated and is the same all the time, which means that for one variable, you can have only one value at a time. It will complain had you write a equal a plus 1, because then it doesn't know if you mean the value before or after. And when I'm saying that everything is updated all the time, is if I'll now define a tangent from A through this circle, then, well, it computed the tangents, but had I change the circle, these tangents are updated, and if there are things that depending on these tangents, like another intersection points, voila, they are updating them at the same time. List is either defined as A, B, C, and now it's the list. And there is a nice command, said A and B and C. Here it is. And there is a nice command called zip that said take on every element of the set. Doesn't have to be points, by the way. For every cent of this point, say type I want to generate a point minus x of p and y of p, where p is every element from the set. So what is happening? Here? Zip command says I want a list, and now for every element p inside the list, I'll do some operation like creating a point whose coordinates are minus of the x point of p and the y point of p at the same time, meaning that it took every point on the list A, B, C and copied it to the other side. Yeah. You can definitely do it. You can also use the sequence command. You'll find it very frustrating that some of the loop commands that you'd expect to find are contradicting it. But I'll show you. Creating a sequence of a set of, let's make it a vector. Create a sequence of vector sinus t. Sinus t tells you the variable, and the variable that I'm talking about is t, and I'll start at 0 and at 2 pi, and the increment is 2 pi over 10. So everybody understand what I created here? So here is a set of points that are, these are the set of points that are all 10 points that each one has the value of cosine minus sine. Going to C, I can go to its setting and change its caption to say show me the name, then show me the definition, then show me the value, and now the point C is defined as A plus a vector A plus V, and here are the coordinates on the screen. It doesn't let me to move it because it's not created by itself. The points that are at the beginning of the independence was A, and when A is moved, then C is moved. Another example of using this zip command that we just had, what happened to it? Here is a zip command. Now L3 is a set of points, and now if I'll do zip for a vector say from F to P, and P is every point on the list L3. Notice the name of the list appeared automatically. It's a set of vectors for V to each one of these points. Matrices that you do want to use, of course, for various reasons. When you type them from algebra, you are writing them as a list of lists, say 1, 1, comma, and list, I just type the first row and then the second row. It creates this matrix M, and sometimes I can just multiply the matrix by the point A and got the results. It will tell me that E is this, the matrix M1 sometimes. And what this matrix is doing, by the way, everybody should know, it's shearing, so it takes each one of the points. If it's not just a point, say I have a segment, automatic name, its name is I, so not what I want to do, no shortcuts are frustrating. Here is its name I, this vector I, and if I'll tell it apply matrix on a M1, this matrix that we just created, on the object I, on the object I, what does it? It creates automatically that I is defined by the 2 points B and H. So the shearing, where did it go? Created the point G prime, and created somehow the points not entirely sure, somehow there is G prime, and here is a vector that is I, just changed. I can ask to here I created on the screen and access to the matrix. It shows me the matrix, and if I want to change it, make it say identity matrix, I change a matrix, and as a result, the application has changed. Everything is always consistent. The opening view, you can open another screen, another window. Both are 2D, called window 1 and window 2. And I can ask for G. If I go to the, for the point G and go to the advanced value, I can ask it to work on, to appear only on the graphics 1 or on the graphics 2 or both. In general, almost done with my demo. I can also open the 3D version where you'll see the whole thing living in 3D, including everything. And basically, if you are submitting the things as 3D, say define a new point as a 0, 0, and 5, that is a Z value is 5, it created the point J that should appear over here on the XYZ instead of the math. And everything that appears also in the XY appears over here. And your matrices, if the matrix was 3 by 3, the matrix that I just defined and I apply it on a 2D vector, it just understands that I'm referring to the 2D in homogeneous coordinates, so it adds a +1 automatically, and the same goes in 4D, applies a matrix on every element in 4D. And matrix multiplication, vector summation happens without you ever paying attention. Okay, and then you can create various animation out of it, like creates for, we had a slider somewhere. We had a slider at some point. So here I'm changing, so we had a slider for S. And if you're, so define an animation that will increase, decrease S, and then you can go not for this one, but if you open, I think you need to download for it the GeoGebra app for a computer, and then you can export GIFs if you want, which is a huge waste of time sink experience because it's never, but it's amusing. Yeah, that's really, and for me as a way, geometric algorithms to see if something makes sense or not, it's the quickest. Okay, that's what homework 2 and homework 3 will look like, and possibly later homeworks as well, and not that much down the line. I still didn't update the PDF, that doesn't appear on the PDF. Let's see what we have as a, this is a JSON file that you'll read into the JSON. You don't need to write, of course, parser for it to get it in the template/library. If you work in other language, every language has a JSON file reading format, and it creates a data structure that reflects what's happening here. Let's speak about things that are relevant for the homework itself. You have the location of the camera or the location of the eye in 3D. That's one of the variables. You have the a point that you are looking at. I remind you, I'll use look at as a specific point. It's not a vector. So the vector that you're looking at will connect the eye to the point you are looking at, and W is pointing backward from this direction. Meaning that if I'm moving, the point that I'm looking at stays the same. Makes sense? When you create videos, the point that you're looking at is staying the same. But essentially, look at the up vector. We talked about it. Up vector doesn't matter which direction you're looking at, up, down. That's what you're calling up. Doesn't need to be 90 degrees to anything. You are using it as a input to create the orthonormal vector UVW by having this there. What is relevant is that, that if you are changing the direction of the app, your image rotates. Okay, if you didn't understand me, it will come up. I'll get back to it later. the field of view angle. It assumes here that you have the same number of rows and columns in the image that you're creating, so your aspect ratio is 1. If you have different numbers, that you can decide whatever you want. You can decide that it's the same angle, because then the field of view, if you don't have the number of pixels, I can understand it in a few different ways. And say that I want a picture with aspect ratio of 1 to 1, and then I'll just assume that it's the same angle of view. Okay, we didn't define what is the angle of view in 2D. Here is my eye/camera. Somewhere here is an image plane with pixels around it, and one of the parameters that I'll give you right there is this angle theta. And larger theta without changing everything just means zoom out. Like I'm going kind of zoom out, but you're seeing more details, and smaller angle is thinner theta, and do whatever you want if the number of rows and columns are not the same. You can either choose to use the same angle, or you'll adjust the other angles that I don't specify. How many pixels do I have in the image that I created? It has nothing to do with how complicated the scene is or how complicated are the billboards in the scene. It's just to say how many pixels should you generate when you're doing the ray shooting. So how many pixels do I have? Well, here is the width of the image, here is the height of the image. So I'll show the parameters today, but essentially what we are doing what I'm doing is creating the image plane that is a template through which you see the rows, you see the columns. When you're creating the image plane, here is a up vector, more or less. That is changing the up vector, just says, how do I arrange the image? That is. Now, the image plane could be in different direction and keep the same up vector. That's the confusing part, if you see it the first time. And the width and the height are just a number of columns and rows that you see over here, and each one will be a pixel that you need to assign a color to. And to assign a color, you are shooting a ray through, okay, meaning that the origin of the ray will be the eye, the camera. The direction of this ray would be the vector that connects the eye to this pixel, normalized or not normalized, up to you. And now you're asking for all the objects in the, that you see over here in the JSON file. What is the first object that I see in the positive direction of the ray? Yeah. No, not exactly. From the side, here is the eye, and I'll put the image plane so that this direction is the angle that I create here is the angle, the field of view angle. So they just tell me how far away this board is created. Now, where is physically this board? It doesn't really matter, because we are just using this board as a factory to generate rays. And once a ray is generated, it has the origin, it has a direction. Put it a bit further away, a bit closer away. It's nice to have to agree about it, but it will not change about it. Okay. That refers to later homework when you treat mirrors or look for illumination. How deep should your recursion go? If your ray hits a mirror, are you just reporting that this mirror has silver color and stop at this point? Are you reflecting from the mirror. 6 will mean it should reflect, and if it hits another mirror, it should reflect. If it hits another mirror, it should reflect, but no more than 6 times. Not relevant for homework 2. Okay, that's the maximum depth. Default color, if you ray hits none of the objects, make it black in this point, whichever you want. And in homework 3 and 4, you'll create shadow and shading. For specular shading, you want to know where is a, well, single source of light in this case, so that's the location of the sun. That's a sun location, and now comes a list of spheres, the direction. Here comes an array of spheres. It will appear then as array. First, the type of the first sphere is well, a sphere. Here is its center, radius, and here is its color. I don't assume that it has I could have also given to it a different RGB value that refers to specular or diffuse. If you look at OpenGL, say, or WebGL, you'll see that you can specify the color of an object using all 3 colors. RGB ambient. RGB ambient just says that's the color of the object. Say RGB of red, not matter is the direction of the light that hits it. Talk about it more when we'll discuss shading. Homework 2, you're using the ambient just to say that's, in this case, this is a mostly, what color? Help? But that would be mostly green with very tiny bit of blue and tiny bit of blue. Okay. Homework didn't entirely decided about homework 3, but most likely you can have mirror balls. So once you hit the mirror, it just means if it said that this mirror, in this case, is if you said that a sphere is a mirror, then once you hit it, then you'll compute what is the direction of the ray that is reflected from the mirror, depending, of course, where you hit the mirror, and depending what the direction of the ray that hits the mirror, then you'll just call the ray tracing recursively, but from the correct point of the mirror that you're just asking what. And as usual, you're just asking for a ray that I generate, what's the first object that I hit. Okay, so here is a list of spheres. Here is a list of billboards. For each billboard, I'll specify where is the lower left, lower upper right, and upper left coordinates, and from all and which file I suggest to put on this billboard. Images that you can put on this billboard, I said you can change the direction. You can change which file it is, and so on, and that's the images that you see on the mirror. And today I'll show you how to do the whole math of moving from the many coordinate systems that we have over here. But everybody understands at least what the scene that I'm going to generate here, that we saw here, like here you have 2 billboards right here, 2 billboards containing the same file. These billboards are not one above each other in 3D because one of them is its normal points to you, one of them is with some angle toward you, this one and this one. And I created this video by doing nothing but changing the direction of the up vector. That's why the image is rotated. Okay, so that was using this image. Another example that I showed you would be so here you also have specular reflection, but so the direction of the sun matters. you see the reflection, the specular reflection of the direction of the sun. Another object is a chessboard over there. And the middle sphere is a mirror, meaning that you can see the reflection of this green sphere in the mirrored image by pressing it once again. Make sense? So that will come a bit later in the course, generate this part, but you see only one billboard. The default color here is green, meaning that everything that I don't hit directly is green. Yeah. Yeah. Yeah, no. You can use any library. You can assume that it's JPEG if you prefer, but I want to see how pixel ij, how do you compute to each pixel ij in the target, you are putting a value in it, and there should be a single command that places a value, and I want to know how do you compute this value, which in this command is just a value of a different pixel in the source. Later homework, you might, or homework one, if you want for credit, you might want to play with anti-aliasing and to say it's not necessarily the exact value of a source pixel. Instead, I'll interpolate between different values of a nearby pixel to create a smooth transition. Okay. Checking orientation, we discussed. Remember, we had the direction of the cross vector of the cross product when I'm going from A to B, that is looking at A cross product B. The vector C is orthogonal to both A and B, and in terms of direction, the vector A cross B is in the way so that if I screw it from A to B using the screw, that's the direction that it moves toward. Okay. Let's go once again about how do I create the orientation. Not again. Let's talk about how do I create the set of orientation. Yeah, you remember that you have recording of everything on the Twitch, except that so far the recording wasn't. The voice as the sound was a bit tricky. Readable, understandable, but tricky, so I'm playing with this. And on previous ones, we didn't have the overhead camera, so the other board. Okay, so we have the eye location. Eye camera is the same thing. And we start from the look at vector. The look at vector, it might be a single point, or it might be a direction. In my homework, it will be a single point that you're looking at the direction, of course, not the camera itself, because, and then the vector W, well defined. W is just pointing in the opposite way from the look at direction. I'm looking at you, so W is toward the wall, toward the other class. Okay, so, and we'll normalize W. And we'll use these names all the time, UVW, that we'll use all over the, and now we are creating a coordinate system of the camera itself. That is, which essentially will tell us how to orient this board, where I'll always orient it so that the direction to the right, arrange it for you. So I'm the camera, U is pointing to my right, I didn't create it yet from the camera, and V is pointing to upward from this part, and minus W goes toward U, W goes toward the camera, me. Okay, and V that we are not there yet might, but doesn't have to be related to the up vector, and V. They'll be quite correlated, but they don't have to be the same vector. Not even after normalizing. Normalize, just to remind everybody, when I normalize a vector, it's confusing term because we have also normal to the surface. That's a different thing. Normalize to a vector, meaning take this vector and divide it by its length, so its length is 1. Okay, 2D, I just created the vector W. Now I want to create the vector U, and every time after creating such a vector, I normalize it. So W is just takes the vector from the eye to the lookat minus a normalize from the head of the camera backward. How do I create U? We said that cross product is our tool to take two vectors and create a third vector which is orthogonal to both of them. So again, the camera from your part is there is a up vector. There is a up vector. It doesn't have to be exactly the lookat. The lookat is somewhere here, so the lookat is changing. So the camera plane, which I'm creating right here, which is a factory to generate rays, the camera plane, the image plane, is orthogonal to the lookat direction. Meaning it's orthogonal to W, and here's the definition. It should also be orthogonal to up. It should also be orthogonal to up. So we had W already, and now I need the vector U, points to my right. U from where you are looking, U points to it. It's me, the camera, and my right is U. So U is orthogonal to both the up, the input vectors that you had as up, and also orthogonal to W. So the order matters. I didn't have W until now. Now I have W, so U equals, and the order matters, up times W, up cross W. Meaning that, remember, W goes to the left. What happened to our screw? Well, if up goes this way and W goes to the back, then if I'm changing my vector, if I'm rotating from up to W, again, from up to W, remember the camera is watching you. Rotating from up to W, what happens to my screw? Screw to my right, exactly as I want over here. So the order matters, and that's U. And now you have U and you have W. Now it's time to generate V that might be up but doesn't have to, times to generate V. How? Again, cross product, once again, cross product of W times U. So if the camera is at the X, Y, is at 0, 0, 0, then W is the Z, the positive Z. U is a positive X going from positive Z to the positive Y. Will give you V, which is a positive Y. So UVW corresponds to X, Y, Z. And they are both right-hand coordinate system because it needs to be so that later a translation rotation matrix I don't have two right hands, but they should be able to snag to each other exactly after translation and rotation. Any questions so far? So once again, good point of confusion is to say good part of confusion is to confuse between the up and W, and it's a good exam question, will give an example where up and W are not the same, where up and V are not the same. Up and V might be the same, but don't have to be. What does it depend on? So again, V and up might be the same vector, but not necessarily. In which case will it be the same? Assuming that they are both, ignoring the length of the vector, just in terms of direction. If W is already orthogonal to the up, which essentially means depending on which I can look at different things without changing the up vector. I can look at different things, but the up vector stays the same, including looking at a lower thing, the up stays the same. Only if what I'm looking at is orthogonal to the up, then W and up points to the same direction. And now we start with a formula that will tell us how to generate pixels out there. Okay, so we'll rephrase this formula a bit further in the next slides. So now I need a factory that will help me generate pixels, either in 2D. Here is this factor is 2D. U points to the side, V is not seen because it's only, you don't see V because V is pointing upward. From where you're watching, V points over here. You see them, of course, in 3D. Here is a camera, and here is the image plane. And the image plane, again, is just a factory to create points, and these points will be used to create directions of rays. And now we'll take every ray and ask, what does it hit? Is the whole thing. So there will be the angle half coming up later. The formula will come. So you can decide that, so I need at some point to decide where I place the image planes. That's where the angle will be. There is a slide coming about this angle. And now I'll say every point along the image plane, either here or here, I'll express as start from the eye, go some distance, yet to be computed, go some distance, capital D will be how far away is the image plane from the eye. Capital D will tell me what is the distance from the image plane to the eye. Of course, changing capital D, decreasing it, will make the camera closer to me, which corresponds to, of course, and again, you can use GeoGebra, you have the link. You can check the code and see that if I'll, by increasing or decreasing alpha, I make the image plane over closer or farther. So alpha is the thing. Actually, it's a bit more than this because you see these are the rays already. So alpha is actually from the last pixels to the from the one extreme of the one pixel to the other extreme of the other one. But if you are screwing up about this part, you will never notice it, so that's fine. If you think about alpha, the angle from the first to the last pixel, yeah. Yes, yes. This is just factory of rays. Once you created the unit vector in the direction of the rays, and the origin of all these rays is the eye, then where is the image plane is completely irrelevant. I just ask what is the first object. You do care, though, you do care about an object that is here. You hit it, but with negative time, you still discover it as hit, but it will be with negative time, so that, of course, doesn't count as a hit. But yes, when we'll use graphics acceleration, Fusion will also say ignore objects that are too close for me. For the math over there to work, I need to decide about some minimum distance. Here, we don't care about it. But you'll see in graphical interfaces that you can specify minimum distance or maximum distance. Or you can specify the same thing, not using the angle and so on, but by using the forced-room that you want to watch it, which is like a pyramid just chopped at the end. And that's an alternative ways to go. You can go from one to the other. Okay, so I'll decide about capital D. How far away is the image plane is away from me? I'll decide about the number of pixels, that's the width of the image. Right? The width that we say is just the number of pixels and sub x. And now I can specify decide that the difference between the pixels might be 1 or might be fraction. Both versions are fine. Anyhow, how do I specify the location of a pixel? Over here is a pixel. Over here is a pixel. Specify how do I get to this point? We now use this formula that tells us vector summation is just like traveling direction, driving direction. Go to this point, then go to this point, and go to this point, etc. How is this relevant? When I write the location of a pixel, I'll tell you, go to the eye. From the eye goes in the direction of W, but what? W points to the opposite direction. W points backwards, so go minus W, minus D, D is a scalar distance, times W. That put me exactly at the center of the image plane. So, this point, right here, the red point over here that you see is just the eye, go to the eye, minus D, the distance that we yet have to compute, depending on the angle, in the direction of W points to me, minus W goes toward you, from the eye to the center of the image plane. And now I need to start generating pixels, which I'll do by, don't go only to WD, but if you decrease constant times U, you will go to the left if it's minus, you'll go to the right if it's plus. So every pixel, the formula, we don't have it here, of R minus B constant times U. That keeps me on the same horizontal plane, horizontal as far as the camera is concerned. The camera might be here, but it keeps me along this line on the image plane, and then I'll add or subtract some constant times V that will take me up and down. And that's how I can generate all these pixels. Okay, so generating all these pixels, similarly generating all these pixels over here. How many are they? I'll assume that that's minus 1 and 1, minus 1 and 1, which by computing the angle now tells me by how much do I change the constants of adding some constant to U, adding some constants to V. So you'll have exactly height many rows and width many columns. That's after you decided about D, and again, computing D depends on the angle. And just to take advantage of this GeoGebra, then I generated a pixel. Now I can generate an array. I don't know which value to place on this pixel. I don't know which value should I place on it, so what should I do? I'll create a ray that emerge from the eye in this direction. I'll normalize it if I want, but the direction doesn't matter. Shoot through this ray, and if the first is red, then the color of this pixel, just copy the color of this object and place it in this pixel. Head I, some point, use another pixel. It will be nothing, and using and head the color would be blue, then the color of this pixel would be blue, the color of this pixel would be red. And again, that's independent of where is if the object is before or after me, or how do I stand with respect to the object. The image plane doesn't matter. This pixel will still be red if I'm at this direction. So it should be red, but you don't see it. Make sense? Okay, so every pixel right here will be, the 1D case will be I, go to the I, minus D times W puts you at the center of the image plane. And now if you assume that this length is 2, between -1 and 1, take J, J equivalent to the X, J divided by number of pixels, the width of the image, number of pixels. Why is the 2 here? Because if you make the math, then for J equal 1, you'll go to the leftmost pixel. J equals NX, you'll go to the rightmost pixel. And where did this come from? Well, the pixel, if you want to be careful, actually the width is -1 till 1. If you think about every pixel as a square or has its own region, so the half over here that is contributed and the -1 just makes it aligned, so the ray is in the middle of the pixel. It will make more sense when we'll actually want to shoot a few pixels through the same, a few rays through the same pixel, which we'll want to do if we want to assume, say, anti-aliasing, or we want to assume that these pixels continue and has a few directions and have lights accumulated from a few sources, so it's not just a single pixel. From this point for homework 2, it doesn't matter where exactly you put this point. It doesn't matter like it doesn't matter for the gray. Yes, sir? Yes, absolutely. So the algorithm as a whole will go by create from the JSON the camera parameters. Good question. The algorithm as a whole, I was too much from trees, you don't see the forest, I was too much in the details. The algorithm as a whole is place the camera parameters, the U, V, W, create them based on the math that we had, decide about what is capital D based on the angle that you want the whole thing to look at, create a set of points, each one with similar formula. Here I just have U because it's 2D. I'll also have addition here, that's a set of points. For each one of these points, create an array, have a different part of the algorithm that takes a specific ray and ray specified by direction and origin, and ask for this ray, what is the first object that I hit? And now the algorithm consists of, in the case of homework 2, the first object that I hit, if I did hit this object, look at its ambient color, RGB, and that's the RGB color that you assign to this pixel. Homework 3, you'll also take the RGB value, but add more specular effect, like asking, is this in the sun, and what's the normal to the direction of the light So I'll have diffuse and orientation. Okay, if I insist that the length of the image plane is from -1 to 1, and actually I tried it in both ways. You can decide actually that every pixel is distance 1 from every next pixel. So your I and J, when you're looking at, so your formula, some of you might find it more easier. You'll say for Pij, I'll create a I minus dw plus J times U, except that that's not J exactly, it's J prime because it is J prime, which is J minus nx half. Why did I do it? This is J prime, where J prime is J minus number of pixels half, will means that my range starts from minus something to plus something. So when J equals 0, you're shooting away through the center of the image without changing from J to J prime. The way that you're shooting will be in the lower left corner of the image plane. So that's why I normalized it. But some of you will prefer to keep it this way, and then the distance between one pixel to the next pixel is 1 unit of J. So they are unit apart from each other. And then the image plane needs to be much larger and depends on the angle. And it's fine. One of you find it easier. For me, the first time I did it, it was finer. It was easier. The textbook will tell you make it -1 to 1 types, -1 to 1, as usual. And that's a canonical volume. And then this J is, this J prime is actually a number between, J prime will be a number between -1 to +1. Okay, so when J is -1, you're in the lower left corner. It might want to call it a different part. When J is +1, you're completely to the right of the pixel. And again, there is a little correction because you are not shooting exactly through the very rightmost point. You're shooting, the pixel has a little size. That's a tiny correction that it's fine if you'll ignore in your first attempt. So if the length of the image plane is 2, that is going from -1 to 1, then it's very easy to compute how far away from the eye it should be. Alpha is a field of view angle. That's what you get in the JSON file. And what is D? Well, let's look at alpha. Alpha half. Alpha half would be that, what? 1 divided by D is tangent alpha half. Again, you have a right-hand triangle. The edge away from the angle divided by the length of the edge adjacent to the angle, that's a tangent. So 1 divided by D, the length of 1, D is what you need to calculate, is tangent alpha, or D is 1 divided by tangent alpha. Okay, and now you know what is this value of D. Yeah. At homework 2, no. At homework 1, but to follow the textbook, you are But to follow the textbook, you will say for 4 pixels, here is the one extreme of the image plane. So from this point to this point, it's 1, but the pixels, the 4 pixels that I generate here, or the 5 pixels that I generated here, the leftmost one started here, and there are 5 of them, and I shoot the ray through the center of the pixel. So it's a segment of length 2 divided by the number of pixels in 2D, or that would be the width. Okay, and now you can, and to follow the you are using alpha x you are using alpha to determine -d, but you'll still keep it a square of size 1 by 1, even if the number of pixels is not the same. You just have more rows and columns, but the aspect ratio of the image is still 1 by 1, and that's fine. But once you show it to the monitor, maybe, if you mind, maybe it's different, especially if the homework will say I only have 10 rows but 1,000 columns, so it might look funny if you're not doing anything. Okay. And yeah, so that's the formula that help us to compute D. Once again, pixels are at the middle, so pixel 0, 0, I equals 0, j equals 0 will be the lower left corner using this formula here. That takes you to the center of this pixel. And once again, if you don't like that the transition by half, if you decide that the lower left pixel is shoot through actually this corner and the upper right is shooting this corner, I don't care. It's small correction if the number of pixels is large, you wouldn't notice it. Everybody understand what the point that I'm trying to make? Just that if when you're writing this formula to start with, if you don't like the correction by -half and half, ignore it. Yeah, and that's defining the image plane. We did it, and is the field of view or the distance, all related. What is viewpoint, camera, eye, all the same. View direction, look at the center that you are looking at. It is a point on the scene. It's not a vector. That's a look at. We have it, and the up vector are given. And yeah, I'm just repeating it again. Here is the formula. Once again, that's when J runs through the number of the columns. And usually you'll do the same thing. Where is it? Usually you'll do the same thing. Here is a formula for pixel ij. I minus dw plus j divided by nx plus tiny correction times u plus, and now remember, if I ignore this part, then I'm in the case that the number of pixels is odd, then I'm just in the middle of the image plane. Again, if the number of rows is odd, then if you ignore this part, you're just at the center row in the image, and now add this little part, then at which direction are you going? You're going in the V direction, up or down in the image plane. Depending on up, V will move you either here or here, V, and that tells you at which pixel you are. Again, and the 2 over here is just because that you are mapping it into -1 and 1, so the total length is 2. Okay, I think that it's the same thing. Again, yeah, we had it, and you can copy the math from it that you wish, just repeating it once again. Different slides, and yeah. nx divided by difference and ny, the same thing. If you want, keep it of the same aspect ratio or not, that's up to you. If nx and ny number of rows and columns are the same, you can solve it in a few different ways. And the big algorithm, well, to answer your question, for each pixel, compute the viewing ray. You had all these parameters, but now for every pixel ij, compute the rij ray, the ray correspond to this pixel, intersect the ray with every object of the scene, with every object. Homework 3, compute illumination at this intersection, because you'll have shading. Homework 2, you don't. And store the resolution, the resulting color. Homework 2, it's just the ambient color of the object you hit at this particular pixel. A bit more math. I have a sphere. What corresponding to the sphere? Here is a center, C. What does a point needs to be on the sphere? I need to know what is a radius, and all the points around the sphere. I might have more slides that explain it. All the points along this sphere, then the corresponding to this point, let's call it V, then C minus the length of minus V, the distance from the length of the vector. So we start. Here is a point P, here is the center C, V is the vector connecting them. What corresponds to all the points P? The length of V is R, the radius, or since I want to ask what for a point P, is this on this circle or not, and don't confuse circle with a disk. It's a circle or a sphere. P minus C, if P satisfies it, well, this length equals R, or P minus C times P minus C. What is this cross product? P minus T times P minus T, C? Well, Euclidean, Pythagoras will tell us that if I'll take the square root, I'll just get the radius of the square, but I prefer, instead of messing up with square root, which is slow operation, I'll just compute once what is the radius square. So for a point to be on the sphere, P minus C times P minus C minus R squared equals 0. If I want to ask what is the equation of the point in the ball or in the disk, to make it into a, to contain also the points that are inside, I'll replace it with small or equal. The equal part, small or equal. Okay. I have a GeoGebra coming for it, but we don't have to. Well, we are running out of time. So now I have a way P, which is what? The origin plus T times the direction. Well, why am I telling you all of it? Because once you have the camera and the image plane and everything else, you can start generating a ray. And now for such a ray, I want to ask where does it hit each one of the sphere, if at all. So what is the equation of the ray? For some time t, it is the origin, which is the I, plus t times the direction. T is a scalar starting at 0, and then our flies at the I itself, and then moves in the direction of p. If it's also on the sphere, this point P of t is also on the sphere, then this should be satisfied. Meaning that if I replace P by P of t, then what do I get? Here is a location at some point t, even though I don't want t. And we are following the same rule as that we saw when we hit a ray with a plane. I'm not asking first what is the intersection point. I'm asking at which point does that intersection point happens. at which time does the intersection point happen. For the times that I don't know yet, because I wanted to keep as one, as an equation of one parameter, one unknown, O plus this point P of t, again appearing over here, minus C dot product. Minus C minus R square equals 0. When I found the right time that it happens, then that's the time that the ray penetrates the sphere. And you write it down, and when you compute all the obstacles, you are getting d times d, which if you normalize d, the direction, this is just 1, d cross product d, plus something that is usually not 1, 2d times O minus C, times this time t that I don't know. So far I have t squared times a constant, plus t times a constant, plus dot product of two vectors giving me another constant, z minus r squared. So that whole thing is a constant, should be 0 at the same time that I just penetrate the sphere. Let's call this number capital A, this number capital B, capital B. This number, everything here that is doesn't depend on t, capital C. What do we get? AT squared plus BT plus C equals 0. Quadratic equation, discriminant, looking at B squared minus 4AC. And now there are a few options. You can either get that the solution is that D equals, that's a discriminant. It might be 0, it might be negative, it might be positive. Which corresponds to what? Help? What does it mean if the delta, here discriminant, is 0, is negative, sorry. No solution, meaning that my ray hits the sphere completely. What if delta equals 0? There is one intersection point, meaning that the ray is tangent to the sphere, and otherwise there should be two intersection points, which makes sense. Once the ray enters the sphere, once the ray exits the sphere. So that's how you compute these intersection points. And next we have to, speak about how do I define a plane once again, and how do I move, and that's an interesting point. How do I move from finding the intersection points? I'll find the intersection point of the ray with a plane that contains a billboard. Now I need to ask two questions. First, is the intersection point, is this intersection point that I just computed, is it inside the billboard of the bunny? And if yes, what is the pixel of the bunny that I need to retrieve to ask what is the color of this point? White for the ear, black for the background. I'll just copy the pixel from this point, but from this I need to compute, to move from the intersection point in the whole plane to ij that I'll retrieve from the image, and this math I'll show you at the beginning of Wednesday. Very good, thank you.